The ability to design something on a computer screen and then have it manufactured in just a few hours has been made extremely easy thanks to 3D printing. And it's allowed me to make many projects from electric bikes to engines that run off compressed air. But for the past 2 years, I've been working on a new piece of equipment for my workshop, a homemade CNC milling machine. This video is sponsored by JLC CNC. More on them later. 3D printing is known as additive manufacturing, where a part is built by adding material. This can be done by solidifying a liquid resin, like with the Formlabs Form 4L, which can create impressively precise and large parts. Or it can be done by melting a plastic filament through a nozzle, like with the Prusa Core 1, and both machines require a rigid frame to ensure accuracy of the printed parts. But a CNC milling machine has to do the same, whilst also pushing a high-speed cutting bit through blocks of metal. To achieve this rigidity, the frame is built from large aluminium extrusions, which bolt together easily and have a degree of adjustability for aligning everything later. However, when I hit the frame with a hammer, it rings like a bell. So in the off chance it gets hit with a hammer again, I decided to disassemble the frame and fill it with sand and epoxy resin, often referred to as epoxy granite, which will hopefully dampen some vibrations. Whether this will affect the cutting quality is something I'll never know, but it definitely made everything a lot heavier. It's definitely a lot heavier. And this frame creates the mounting points which each 3 axes will travel along. And it's important that each axis will only move in its constrained direction, which is the job of these large linear rails. And in order to drive each axis, these large ball screws are used to transfer the rotational motion of an electric motor into linear motion. Though the actual motor of choice is a NEMA 34 stepper motor, which has far more control compared to a handheld drill, and each axis will have its own motor to move the cutting bit in all 3 dimensions. The 4th motor on this machine is the spindle, which is a very different type of motor, as it's designed to spin sharp cutting bits up to 24,000 RPM, with a power output of 2.2 kilowatts. And the wires for these motors can neatly pass through a cable drag chain that runs along the back of the gantry. Speaking of the gantry, this design of CNC machine is known as a fixed gantry design, which means it needs a work plate that moves back and forth along the y-axis. This is very similar to some 3D printers like the Prusa Mark IV, though my choice of design wasn't directly inspired by this. Many large CNC routers have a moving gantry design, which is great for cutting large sheets of material, but the design can lack rigidity due to the gantry having to move, whereas a more precise milling machine, often used for metals, will have a much smaller cutting volume that moves in both X and Y, whilst a spindle is attached to a rigid pillar that moves just up and down. So my machine is halfway between the two, where the X-axis runs along a large rigid gantry that is fixed to the base of the frame, and also carries the Z-axis, allowing the build platform to be relatively large as it's able to pass underneath the gantry. This should hopefully be capable of cutting small precise parts for my projects, whilst also being able to cut sheets up to 500mm in both X and Y. But to control all these axes, we need a control board, which I've chosen to go with the Duet 3 6HC board, as it was recommended by a fellow YouTuber and CNC builder, Ivan Miranda. This board has some cool features, like high current motor drivers, allowing the motors to connect directly to these pins, and an Ethernet port for connecting to the internet, so it can be controlled by any device with an internet browser. Perfect. And once all the electronics were set up, I built a frame around the machine using some more extrusions, which will hold some thin sheets of aluminium to create an enclosure, as I don't want my workshop to get covered in metal chips. And with the addition of some LED lights, the machine is starting to look rather professional. I then added a clear polycarbonate door to the front and a side bracket for a cheap touchscreen monitor that will be used to operate the machine. And finally wired up the spindle, which if you ever build a CNC machine, don't leave a loose collet nut on the spindle, especially if it spins the wrong way. The complete build of this machine is documented in far more detail over on my second channel, where I also go through the initial test cuts, which included turning the huge aluminium build platform into a fixture plate by drilling and threading 178 holes that make it easy for clamping down parts, as well as attaching a milling vise. This whole machine cost me £3,955, or just over $5,000, and took a lot longer to build than I initially expected. And this cost includes everything from the essential components like the frame and linear rails, to the add-on components like the touchscreen monitor and handheld jog wheel that allows me to move each axis in increments as small as 0.01 of a millimeter. However, if you've been subscribed to my channel for a while, you'll know I already have a CNC router, which I bought about 7 years ago for a very low budget and from a guy who must have had a phobia of thread lock, so it's not the most precise or reliable machine. However, it did allow me to make some of the large aluminium plates used to make this new machine. But if you don't have a CNC and need to make some parts, then I highly recommend the sponsor of this video, JLC CNC, who offer fast and affordable CNC services. And don't worry, you don't need to create a professional engineering drawing. Simply upload your 3D model to their website, then choose from the selection of options they offer, like the material, surface finish, or any holes that require threads, and get an instant quote. Plus their turnaround time is only 3 to 5 business days. These large plates arrived at my door just a week and a half after placing the order, and I'm very impressed with the quality, especially when compared to the plates I made myself. And these new plates fit perfectly with my design and provide a strong brace between the gantry and the Y-axis on my machine. Honestly, I wish I'd ordered from JLC CNC a lot sooner, because their service is excellent, and although I now have my own CNC, I will definitely be ordering from them again, because they offer services like 5-axis machining and other materials like stainless steel. So if you want fast, affordable, custom-made parts, then don't miss out on their special offer of $70 off your first order by going to the link in the description down below. So 2.5 years after I initially started designing this machine, it's finally finished. So let's make an engine. This is a block of aluminium that is slightly larger than the part we need to make, and we need to program the machine with a set of instructions known as Gcode. Gcode is essentially just a list of coordinates that the machine needs to move to. So it could say something like move to Y5, which is 5mm forward, then move to X10, so 10mm right, then Y0, and then X0, and now the machine has cut out a rectangle. But there's a catch, because these instructions are all relative to the 0 point, often referred to as the work offset. Now for cutting this rectangle, the work offset isn't that important, though it's probably best to move it to the bottom left corner just to save wasting the whole sheet of material. But if we want to cut something much larger, that's close to the size of the sheet, it's very important that the position is set correctly. To do this, we can manually move the cutting tool until it just touches the block of material, and then after accounting for the radius of the tool, the work offset can be zeroed on that axis. But this can take several minutes to do accurately on all 3 axes. And an alternative to this is to use a touch probe. There are commercially available touch probes, like this one that mounts in the spindle and is wired up to an input pin on the control board. But I don't like having to remove the cutting bit every time a part needs to be probed. So I did some prototyping and came up with my own design. This part here is the mounting bracket for the probe and requires 2 45-degree angled faces, which the probe will sit against to ensure it's always seated in the same position. And this mount is attached to the machine with a few 3D printed spacers to electrically isolate it from the frame. Then the probe itself is just another block of aluminium with the small probe needle I took from the commercial probe, and this attaches to the mount with a small magnet. But in order for this probe to communicate with the control board, I clamped a wire to the rear of the mount and wired that into a signal pin. Then I attached a ground wire to the build plate, and hopefully when the probe touches a part, it completes a circuit, and the control board saves a position. Then I can measure and program in the offset from the probe to the spindle, and then it will save exactly where the work offset will be. I also pre-programmed a few different probing sequences, like being able to probe all 4 sides of a part to find its center, and it works surprisingly well for being so simple, though probing non-conductive materials may cause some issues. So let's finally make a crankcase. I've still got lots to learn when it comes to machining, so the parameters make the machine sound a little rough sometimes, but overall I'm happy with the quality of the parts this machine can produce. The top face of this part is going to be the rear of the crankcase, so it needs to be bored out to make space for the crankshaft and bearings. And I drilled some mounting holes on the rear for testing the engine later, which can be threaded with a cutting bit called a thread end mill that have these angled cutting teeth to cut a perfect thread, which saves a lot of time and effort compared to hand tapping the holes. And then this side of the machining process can be finished off with a chamfer tool to add a 45-degree angle to all the corners. Once complete, the part needs to be flipped to machine the top side of the crankcase, which requires reprobing as the location of the part has now changed. And it's important we get the work offset correct, as this new hole will be the location of the cylinder. To mount the cylinder, I've chosen to use a threaded hole, specifically an M16 by 1mm pitch thread, which is so satisfying to cut with the thread end mill, and the reason for this thread will become clear later. So after another quick chamfer cut to deburr the edges, the crankcase can be flipped one last time to machine the front side, which needed probing, facing, and a lot of material to be removed, to bring it down to a nice cylindrical shape, as well as boring out the centre where the output shaft will pass through. So the first part of the engine is now complete, which took about an hour to machine. And whilst I was making it, I also 3D printed the same part using resin on the Formlabs Form 4, with a print and finishing time of about 2 hours. As well as printing a version on the Prusa Core 1 using PLA plastic, which took just 22 minutes. However, this comparison isn't exactly fair, as the setup time for the aluminium part was about 2 to 3 hours. This is because unlike the 3D printers, where I can simply import a 3D model, change a few parameters and click print, the CNC needs every single cut to be pre-programmed, down to the depth of cut, the speed at which the tool needs to move, or even which tool to use. And if you get it wrong, it's very easy to break things. So although the aluminium part looks cool and will be the strongest, for parts like this crankcase, which doesn't necessarily need to be the strength of aluminium, it would have been far easier and cheaper to 3D print. So why am I now deciding to make an air engine out of aluminium when the plastic engines I previously built work just fine? Well, partly it's because I want a project to test out my new CNC mill. But I also believe that increasing the operating pressure of these engines could help with the efficiency and power output. Specifically for running the engines off liquid CO2, which at room temperature is about 900 psi. However, unlike regular compressed air at 900 psi, which gradually decreases in pressure as the engine runs, the liquid CO2 should maintain 900 psi until all the liquid has boiled off, acting almost as a self-regulating source of gas. Now this specific engine will hopefully run off just regular air at 100 psi, as I'm still learning the best methods to manufacture certain parts, and have lots to figure out before making the CO2 engine, especially when it comes to the piston and cylinder. Because whilst the CNC mill is very good at cutting straight lines due to the linear motion system, it struggles a bit when cutting circles. This is partly due to the precision limit of the drive motors, but also due to the coordinate Gcode system that the machine must follow. As mentioned earlier, to cut a square we need 4 lines of coordinates, so to cut an octagon we need 8 lines. And if we keep increasing the number of coordinates, we get closer and closer to a circle. However, even with 150 lines of code, which is what the CNC software generated, it's still far from being a perfect circle. Ideally, this could be machined using a lathe, which makes perfectly round parts by spinning them and using a stationary cutting bit. But what about if we do the reverse, by spinning the cutting bit around a stationary part? To do this, we need to make a custom tool that offsets a cutting bit by the radius of the piston. So this tool has a bore down the centre, which is larger than the piston diameter, and some material must be removed from the side to mount the cutting bit. However, this tool will eventually be mounted in the spindle and spun up to about 10,000 RPM, so it needs to be balanced well, which isn't helped by removing a large amount of material from one side. To counteract this, the design looks very unnatural, as the lack of material on this side is balanced by removing material from the other side. And I designed this using the centre of mass tool in my CAD software, so let's hope it balances in reality. It's then flipped on its side to machine a tiny triangular slot, as I plan to use one of these insert cutting tips, which will be mounted with a small bolt. so a hole needs to be drilled and tapped. Though I don't have a thread end mill small enough for this thread, so I tapped it by hand. And literally 3 turns after I stupidly stopped recording, I broke the tap. This tap was well and truly stuck, and it's too small to remove from the part without damaging it. So I had to machine a whole new part, and this time I chose to tap it from the other side, which worked far better. Then the part can be flipped one last time to remove all the remaining stock material, and a hole can be bored through the centre, which needed to be tapped with an M10 thread, so I can use a 12mm diameter shoulder bolt as the main shaft. So with the small cutting bit attached, the new tool can be loaded into the spindle to see if we can achieve a perfectly round piston. Not only did the tool balance well, but the finish quality on the piston looks much better, as the tool takes care of the circular cutting and the CNC just has to move vertically. Now we just need to do the same for the cylinder, which fortunately there is a tool for. This is a boring tool and it works the same as my DIY tool, but for internal diameters. And unlike my tool, its diameter can be adjusted by turning this dial. So to make the cylinder, we can cut an undersized hole with a regular end mill, and then use the boring tool to widen it to the correct diameter. This does take quite a few cuts to get the bore just right, as I want the piston and cylinder to be as close to being airtight as possible, removing the need for any piston rings. And it's pretty close. However, there's a slight issue with this machining process, as it leaves horizontal lines in the cylinder and on the piston, which can cause friction between the 2 sliding surfaces. To fix this, I bought some lapping compound, which is an abrasive paste, and when combined with a custom 3D printed tool that applies an internal pressure to the cylinder, should be able to polish the cylinder smooth. Now this engine is about as basic as an engine can get, and relies completely on my assumption that the piston seal will make it work. This is because the air inlet valve will be a simple ball valve, which is opened by a small pin that's machined into the top of the piston. But it's important that the piston opens this ball valve as close to the top of its stroke as possible, because due to the natural geometry of a crankshaft, less torque will be required to open the valve if it's as close to the 12 o'clock position as possible. However, if the piston and cylinder seal isn't perfect, and air can escape, then the valve needs to be open for longer, massively reducing efficiency or even preventing it from running. The other aspect to consider is the compression caused by the piston travelling up the cylinder, which is important for the efficiency of a real combustion engine, but could cause issues with this air engine, because if the compression stroke creates a higher pressure than the supply pressure, it'll just pump air back into the supply tank, and we'll have a mini compressor instead of an engine. Now because this engine runs on just air, you might be wondering, why am I cutting cooling fins into the cylinder? Well, when I eventually power an engine with liquid CO2, the expansion of the high pressure gas can cause a large drop in temperature, in the same way an aerosol can gets cold when you spray it. Therefore these fins are actually to heat the cylinder, which should help the gas expand and hopefully increase performance. So with the piston and connecting rod attached to the crankshaft, the cylinder can be mounted with its threaded attachment, and a tiny O-ring with a 3mm ball bearing can be inserted into the cylinder head to make the inlet valve. So with the engine fully assembled, it can be attached to a custom mount, and a large propeller will act as a flywheel. Then with a compressed air supply attached to the cylinder head, will it run? Not quite, but this is why the cylinder is threaded into the crankcase, and by turning the cylinder we can adjust the inlet valve timing. So if the cylinder is lowered, the valve will open earlier and close later, but if it opens too early, the engine will backfire. Though even with multiple attempts at fine-tuning the valve timing, it still wouldn't run. So I decided to inject some mineral oil into the exhaust ports, which seems to help a lot. And with a few small adjustments of the valve timing, it seemed to hit a strange power band. though I need to figure out how to lock the cylinder thread once I find the optimal position, as the elastic torsion in the pressure tube slowly changes the valve timing. But I couldn't be happier with this first prototype, as I've learned a lot during the process of making it. And as mentioned earlier in the video, the whole build of my CNC machine was documented in greater detail over on my second channel, Tim Station. So if you're interested in seeing any other extra content that I've put together, then go and check it out and subscribe. Thank you for watching.